Hey everyone, I'm Max, and we're Group 10. We're going to be talking about approximation techniques and its applications. So, why are we doing approximation at all? Because it is hard to find optimal solutions to NP-hard optimization problems efficiently. However, it is possible to find near optimal solutions using approximation algorithms and techniques. So, what is approximation exactly? For the context of this presentation, NP-hard optimization problem will be the primary focus. And an NP-hard optimization problem is either a minimization problem or a maximization problem. Each feasible solution of the problem comes with an objective function value, which is a problem-specific value one is trying to minimize or maximize. A feasible solution that achieves the optimal objective function value is an optimal solution. An approximation algorithm generates a polynomial time feasible solution with an objective function value close to the optimal one. So by saying close, the approximated objection function value is within a guaranteed factor of the optimal one. So how do we evaluate an approximation? How do we know how good it is? We're going to be using the definition of approximation factor, which is the ratio between the cost of the proposed solution and the cost of the optimal solution. We say an algorithm is a factor X algorithm if it has an approximation factor of X. So let's look at a simple example, which is a very commonly discussed problem, which is called set cover. So this is the formal definition of the problem. Given a universe U of n elements, a collection of subsets of U, S, which includes subset S1 to Sk, and a cost function C, the input would be subsets of U, and the output would be a cost of covering elements in S, which is in the domain of positive rational numbers. The goal here is to find a minimum cost subcollection of S that covers all elements of U. So the intuition here is you use the greedy algorithm, which I'll be talking about in the next slide. So greedy algorithm iteratively picks the most cost-effective set and remove the covered elements from that set. We repeatedly do this until all elements are covered. So we define the cost effectiveness of S to be the average cost at which it covers new elements. So let's say C is the set of elements already covered at the beginning of each iteration. Cost effective of S would simply be the cost of the newly added set S over newly added elements in that iteration. So it's simply the difference between S and set C. And the string chart below is the official algorithm formally written. So how do we put greedy algorithm into some practical situations? One of the main scenarios would be deciphering human DNA. So the human DNA can be viewed as a very long string over a four-letter alphabet, namely A, C, G, and T. Scientists are attempting to decipher this string. Since it is very long, several overlapping short segments of this string are first deciphered. Of course, the locations of these segments on the original DNA are not known. It is hypothesized that the shortest substring, or superstring, which contains these segments as substrings, is a good approximation to the original DNA string. So the formal definition would be as follows. Given a finite alphabet and a set of strings from S1 to Sn, the goal is to find the shortest superstring that contains each string in big S as a substring. Without loss of generality, we may assume that every string in big S is mutually exclusive. So no two substring is the same. So let's put greedy algorithm into practice. So we define the overlap of two strings, S and T, as the maximum length of a suffix of the first string that is also a prefix of the second string. So for example, if we have one string ABC and the second string as BCD, then the overlap of these two strings would simply be ABCD, right? Because the maximum overlap, if we overlap them as much as possible, then BC will be the maximum overlap. So ABCD is the resulting string. So greedy algorithm maintains a set of strings. Initially, T will simply be the set of all substrings, right? And at each step, greedy algorithm selects two strings from that set that have maximum overlap and replaces them with the string obtained by overlapping them as much as possible. So basically, as the example I was talking about earlier, if we pick ABC and BCD from T, then we simply remove these two strings and put back the resulting string, which is the ABCD, back into T. So we repeatedly do this after n-1 step. T will simply contain a single string. Clearly, this string fulfills the requirement that it covers every substring, right? But this is not good enough. So let's look at a concrete example of why this is. So consider an input of the following three strings, A followed by KBs, KBs followed by the C, and K plus 1 Bs. So following the greedy algorithm, if we pick A followed by KBs and KBs followed by C in the first iteration, then the maximum substring would be C, A followed by KBs and then a C, right? And we put that back into T. So if we pick so the only remaining two options would be A followed by KBs, C, and the last string, which is K plus 1 Bs. So if we overlap those, obviously there's no overlap, right? So the resulting string will simply be the concatenation of those, which is A followed by KBs, and then C, and then K plus 1 Bs. So obviously this superstring fulfills the requirement in a way where it contains all three strings, right? So the length of the string is approximately 2k plus 3, right? Um, but as you can see, the shortest substring in this case is actually A followed by k minus k plus 1b and then C, which has a length of k plus 3, which is almost half as long as what we got from the greedy algorithm, right? So that's why in this extreme case, it is not good enough. So what do we do about it? Um, so so what we do, let's look at this more, I guess, complex example. We have these three strings S1, S2, and S3. For each pair of S1, S2, and S3, we denote this pi IGK as the shortest superstring for pi I and pi j, where the overlap includes k bits or like positions. So in this case, if we try to find the shortest superstring between 001, which is S1, and 01101, which is S2, as you can see, the maximum overlap possible would be 2 digits, right? Which is 01, which happens to be the last 2 digits for S1 and the first 2 digits of S2. So if we overlap those two, we will get 001, 101, right? And this is basically pi 122. And we define the cost of this pi as the length of the string. So if we overlap S1 and S2, the cost would simply be 6 in this case. And we do this for all individual substrings and all superstrings. So now the question becomes, given U, which is obviously S1, S2, and S3, and the set of substrings that contains all individual strings and all superstrings. And cost function would simply be the length of the string. And the goal is to find a minimum cost subcollection of S that covers all elements of U. So let's move on to another very common problem, which is metric traveling salesman problem, TSP. So the formal definition of the problem is as follows. Given a complete graph with non-negative edge costs, find a minimum cost cycle visiting every vertex exactly once. So a cycle is essentially a path that starts and ends at the same vertex, which is pretty obvious. So by saying complete graph, we mean an undirected graph where every pair of distinct vertices is connected by a unique edge. So the metric in this metric TSP problem is triangle inequality, which means that the direct connection from A to B is never farther than the route via some intermediate point C. So if we want to go from A to B, the shortest or the path with the least cost is always go directly from A to B instead of going to some intermediate route C and then go to B. So a simple solution for this metric TSP problem is as follows. We find a minimum spanning tree of the graph. So a minimum spanning tree can be computed in polynomial time using, for example, Kruskal's algorithm or Prim's algorithm. And after that, we double every edge of the tree to obtain a Eulerian graph. So by definition, a graph is Eulerian if all vertices have even degree, which means every vertex have an even number of edges connecting to it. So after we find the Eulerian graph, we find a Eulator of the Eulerian graph. And Eulator is basically a cycle that uses each edge exactly once. And the last step would simply be output the tour that visits the vertices of the original graph in the order of their first appearance in the Euler tour. So let's look at a simple example of this solution. So this is already a minimum spanning tree, which includes one, two, three, four, five, six, 6 cities with the cost of going from one city to another, right? And we double the edge here, as you can see. You go from Arlington to Medford, and then Everett, and then Somerville into Belmont, Cambridge, back to Belmont, and Somerville, and Arlington. So as you can see, each edge is doubled here, right? Because you can go from one to the other and then going back. So we follow the order of how each city appeared in the cycle. So we go from Arlington, from Somerville to Medford, and then Everett, and then we go Belmont into Cambridge, and then back to Arlington because it is a cycle, right? Each city here is gonna appear only once, obviously. So this is a example of how this solution essentially works. So, but the previous approach is obviously not the best one. A better approach would be, instead of doubling every edge in the minimum spanning tree, we compute a minimum cost perfect matching on odd degree vertices and let the union of the matching and the tree be the new Euler graph, and we do the rest the exact same way. So let me explain how perfect matching works. So a matching in a graph is a set of edges without common vertices. A perfect matching is a matching in which each vertex of graph or in the graph appears exactly once. I'm going to provide a concrete example for this better approach as well. So this is the complete graph. Obviously, each edge weights obey like the metric, which is the triangle inequality, right? And we calculate the minimum spanning tree, which is like this. We do take out the set of vertices with odd degree. As you can see, the 4 vertices on the edge all share a degree of 1, which in the middle one is a degree of 4, which is even. So we exclude that for now. And we form a subgraph of using only the vertices on the corner or in the corner. So a subgraph is basically using all these vertices in the subset and all edges connecting pairs of vertices in the subset. So we only include vertices in edge connecting to these 4 without taking care of the middle one. And we constructed a minimum weight perfect matching in this subgraph. We labeled them as A, B, C, D, and E. And we basically union the matching and the spanning tree to perform a Eulerian graph here. And this is the Euler tour. So the tour can either go from A to B to C, and then A, and then D, and then E, and back to A. It is equally the same if you go from A to B to C, and then A to E to D, and then A. It is essentially the same. You can take either way. So we remove the repeated vertices. The graph would look something like this. So the next, the last topic I'm going to talk about is randomized rounding. But before we talk about that, it is beneficial to introduce some of the core concepts in randomized rounding. So a linear program is basically find the optimal solution, either minimizing or maximizing to a linear function with certain constraints. If we look back to the problem of set cover, the first bullet point is basically the formal definition we just talked about. But in addition, because we are doing the linear program, right? And here is the constraint in the last bullet point here. So we introduce an indicator variable xs associated with each subset in the big S. So xs is basically 1 if the subset is selected, or it's 0 otherwise. So now set cover problem can now be formulated with the linear program. The goal is obviously try to minimize the cost. So it's like the sum of cost times whether it is selected or not. If it's 0, then obviously the cost doesn't matter. If the set is indeed selected, then we add the cost together, right? Now, this minimization includes the constraint of here is basically xs is, so basically every element in U has to be covered, is what this first constraint is doing. And obviously, we define the indicator variable to be either 1 or 0 for each subset in big S. So we're doing LP relaxation by removing the constraint that xs has to be one of the two integers, 0 and 1. So now the new LP will be the relaxation of the original linear program. The goal is obviously the same. The first constraint is the same, but you can see as this in the second constraint, we only constrain xs to be greater than or equal to 0, without actually being one of the two integers. So a solution to this linear program is what we call a fractional set cover. I'll show in the next example as why this is called fractional and why this might be better. So why might fractional is be better? So we consider this following example. The universe of all elements is E, F, and G. We have the set at big S, which contains EF, FG, and EG. And obviously, for simplicity purposes, all subset have equal cost of 1. So if we do the normal integral set cover solution, we'll basically be picking any two sets from the big S. You can pick S1, S2, you can pick S2, S3, or you can pick S1, S3. They literally do the same thing, right? They are the only ways to cover all elements of E, F, and G. And obviously, since each subset costs 1, picking any two sets from the big S costs 2, which is the total cost in this case, right? But if you look at the fractional set cover solution, we pick all three sets, S1, S2, and S3, to the extent of 1.5. So basically, if you pick S1 to the extent of 1.5, you essentially have one half of E, one half of F, right? If you pick one half of S2, you will have one half of F and one half of G. So now you have one half E, the whole F, right? And then one half of G. If you add one half of S3 on top of that, you will have one half of E right here in the S1 and one half of E in the S3. So you make it a complete E. And similar case happens for G in half of S2 and half of S3. Now you have all three elements covered to the extent of 1, right? But the cost is obviously if you pick all three sets to the extent of 1/2, each subset will take up cost of 1/2. So the total cost will simply be 3/2, right? And this is obviously better than integral set cover solution since we are trying to minimize the total cost, right? So this is why LP rounding can be used to solve the set cover problem as well. So we find an optimal solution to the LP relaxation problem as something I just showed earlier. And we pick all sets for which xs equal to 1 over f in this situation. So f is basically the most frequent element in the overall set. And randomized rounding is one step above that. Is basically consider each xs, the indicator variable, as a probability to include the set S. So this set is not the overall big S. It is obviously the every subset in the big S. So for each set, include it with probability xs, and we do the same step repeatedly until all sets are covered. So this is randomized rounding, and that's it for me, and I'll pass on to my colleagues here.
Thank you, Max, for that insightful overview of common problems that rely on approximation algorithms. Now let's dive in deeper with another interesting example. As discussed earlier, approximation algorithms are used to find good enough solutions when it might be too computationally expensive to find the optimal solution every time. As we have studied, the dynamic programming and greedy algorithm both comprises of these three properties. They are deterministic, they are always correct, and the worst case is bounded by a polynomial function related to its input size. So we have looked at algorithms that had complexities like big O to the n, big O n log n, big O n squared, and big O n cubed. But what about problems that have complexity like big O2 to the n, or worse, big O n factorial? These problems are extremely difficult to actually come up with a solid answer in a reasonable amount of time. So, of the three properties listed above, we want to relax one of them so that we can come up with a good enough solution, not necessarily the optimal solution in order to solve the problem in a fast enough time. So, we are going to relax condition number 2, the always correct. So we're going to come up with an approximation solution as opposed to the optimal solution. So approximation algorithms are typically applied to a min or max problem, otherwise known as optimization problem. And we can prove that it's close enough to the actual min or max value. So how close do we want it to be? Let's say min example, which I'm going to go over right now. So let's assume that C star I is the optimal solution, the minimum value for an input I, and Ci is the value returned by the approximation algorithm. When we put them into a ratio, we have Ci over C star I, which is less than or equals to k being a constant value. Ideally, we'd want k to be equal to 1. However, it's unlikely with an approximation that it would be equal to 1. That would be the best case scenario, so we want it to be as close to 1 as possible. It'll never be less than 1, so it'll be as close to 1 from the positive side. So maybe 1.6, maybe 1.8, perhaps even 2, but the closer it is to 1, the more accurate our approximation algorithm is. The beauty of this system is that Ci that was calculated was determined by a polynomial time algorithm, so we found Ci in relatively quick time. So now let's go over a specific example that is called the center selection approximation algorithm. So let's say we have a map like this, and all of these green dots represent cities. Let's say an online company wants to place warehouses in a way that serve all of these cities in the most effective way. So we'll have K warehouses, and the goal is we want to minimize the radius r between the warehouses and the cities so that the delivery trucks don't have to travel too far to deliver the goods. So now we wanted to find what it means to be the radius to a warehouse. So let's say we have these three cities and there was a city here where the warehouse is currently located. If we were to connect the cities to that warehouse, the longest line is the radius between the warehouse and the city that it serves. So in this case, it would be this line here denoted by the arrow. So let's look back at the map of cities that we have looked at earlier. There are far too many ways to place warehouses, especially as number of city increases. So this map is relatively small, but if it had a map with thousands of cities or even million of cities, then there would be too many ways to place warehouses to try out. So we do not know a deterministic, always correct polynomial time algorithm to determine the warehouse placement. So the best we can do is use an approximation algorithm. So initially, we don't know what the radius r is. So we have to assume a value for the radius r. Let's say it's equals to r. We want to let C be the set of city, C1, C2, C3, all the way to Cn. And we also want to define C prime, and initially it will be equal to C. We let W be the set of the warehouses that we have placed. And initially before placing any warehouses, W is equals to 0 or empty. And our target K value is 5. So we have only at most materials needed to build 5 warehouses. We can't build any more, so let's see if we can serve all of the cities with at most 5 warehouses. So I've placed the C prime values and W in the corner so we can update them as we go along. Also you can see the length of R and the length of 2R for comparison. And here is the algorithm, and I'm going to go over it in just a moment. So let's say these are our cities, city 1 to 15. So while C is not empty, we pick any city in C prime and add it to W. This will be our first warehouse placement. Then we want to delete all the cities in C prime that are within 2R, so 2 times the radius, from the city that we have picked to place our warehouse. So let's get started. So let's pick city number 3. So I can remove 3 from C prime and add it to W. So now 3 is picked. I want to draw a circle that is 2R radius around it, so the cities 2 and 6 fall within this radius circle. So we can now remove them from C prime, and now we can pick the another city. So let's pick 13. So now I can remove 13 from C prime and add it to W. Now I want to draw a circle that is 2 are around 13, and we can see that 15 and 14 fall within this circle, and we can delete those from C prime. Next, we'll pick 4, so we can now remove 4 from C prime and add it to W, and now draw to our radius circle around. Cities 1, 5, and 8 fall within the circle, so we can delete those from C prime. Next, we are going to pick the city number 9, so we can now remove 9 from C prime and add it to W. And we can now draw the circle that is 2R around 9, and we can see that cities 7, 10, and 12 fall within the circle, so we can remove them from C prime. And that's left is city 11. So we pick the next to make our last warehouse placement. So we can now remove 11 from C prime and add it to W, and trivially we can draw the circle around it. However, since it is the last city, we are not selecting any more cities to delete. C prime is now empty and the algorithm is complete. The next part of algorithm is if the number of warehouse in W is less than or equals to K, then we can output W as a valid solution. So because our K is equals to 5 and we have 5 elements in W, this would be a good enough warehouse placement to output as possible solution. But if the number of W that we have placed in our algorithm is greater than K, then no set of K warehouses exists, such that all cities are within the radius to some warehouse, so we would need to increase our assumed radius size and try again. Why does this algorithm work? Suppose we know the optimal warehouse placement, let's call it W star. And let's say this city here with the black circle around it is one of those optimally placed warehouses. And these circles outside are the cities that it serves. This line here is the radius of the city. So let's say our algorithm in its random selection of cities picked this one here with the red circle around it. If we draw the 2R radius circle around it, we would cover all the cities that are served by the optimal warehouse location. So all the cities that the optimal warehouse location covers are within this 2R radius circle of the warehouse picked by the algorithm. Each city that the algorithm picks to be a warehouse site is within radius R to a warehouse site in W star. So the algorithm pick at most K warehouses and the distance of any city is at most 2 radius of each warehouse. The warehouse set W that the algorithm picks may not match the optimal solution W star, but it's a good enough approximation. So that concludes the center selection algorithm. There are many real-world applications of K-center algorithm. Few of them are in public health clinic, where it can help with optimal placement of healthcare facilities like hospitals and clinics. That would ensure better healthcare access and reduced patient travel time. It is also helpful in telecommunication and network design by determining location for cell towers and base stations. This would improve network coverage, reduce dead zone, and enhance connectivity. It is also very plays important role in emergency services and disaster response by strategic positioning of emergency response centers, fire station, and police station. This would minimize the response time during emergency for increased safety. Now I would like to call Abhishek for the further presentation to discuss upon the approximation algorithm.
Hello all, my name is Abhishek and I'll be covering the standard T problem for our topic approximation algorithms and its applications. We will go through the rundown of what I will go through my presentation. So first we will cover general definition of the standard T problem and what are some good and bad examples of the standard tree approximations. In that we will cover Euclidean standard tree problem, metric standard tree problem, and the general standard tree problem. Then we'll see a theorem and a proof for the metric sanity problem, and how can we use that proof to solve the general sanity problem itself. So basically reducing the general sanity problem to a metric sanity problem and then solving it suboptimally. And then in the last, we'll see some applications where the sanity problem is getting used in real world and what are its benefits to the real world and why do we study the sanity problem in field of approximation algorithms at all. Okay, so let's begin. So the formal definition of the sanity problem is like, assume that we are simply given an arbitrary graph with edge weights where some of the vertices are required vertices and some of the vertices are standard vertices. We'll go in detail like what are the required vertices and what are the standard vertices in the next figure. So the assumptions for this definition are like we have a graph G with vertices V and edges E, and the edge weights W, and all the edges span across the required vertices, and a set of required vertices belong, we'll call them R. They belong to like all the set of big set of vertices V, and a set of standard vertices which are again subset of the big subset of vertices V. So the general sanity problem is itself is find a subset S dash from the set of all the standard vertices and a spanning tree T of R union uh, uh, S dash along with edges E of minimum weight. That means the weight of the tree equals to R union S dash along with edge. That's defined to be basically summation of U comma V uh, with all the edges and with the edges DUV, basically minimizing it. So let's understand it using a simple graph. So we can see in case of Euclidean matrix, we have like this small tree of a triangle, right? So we have like three vertices and three edges having weights of one each. So in this case, this Steiner point here, like it's the optimal solution, right, for the Steiner point itself. So it's considered in the center. So if you're looking at the minimum, sorry, the metric Steiner tree, the optimal solution for that is considered as the minimum spanning tree solution, which is polynomial time. So the cost will be of connecting all these required vertices. Let's say the required vertices are three in this case for the triangle one. Then we'll obviously need to cover all those three vertices. So the minimum cost that we can do it in is two. Basically, we're connecting one and one, so the total cost is two. But an optimal solution would be like having a Steiner point in the middle, and then the total cost will be root 3. In case of rectilinear metrics, let's say we have 4 points having like connected in a square dimensions. So if you want to connect all these 4 points and having the, let's say, the edge weight between these 2 points is 2, then the minimum cost to connect will be basically 3 edges. So that's each edge is 2 weight. So it's going to be total of 6 weight. And for this also the Steiner optimal solution would be a cost for having a Steiner point in the middle and all the edges connecting through that, each having a weight of 1. So that would be a total cost of 4. So that's how the Steiner problem is. Basically minimize the total weight of the graph, finding a minimum spanning tree and just minimizing the total weight. Yeah. So let's go through the what are like good or bad examples for the Steiner tree approximations. There is a simple and natural heuristic for solving the Steiner problem. Just ignore all the standard vertices and simply find a minimum spanning tree for the required vertices. This is like a simple heuristic, basically finding the minimum spanning tree. That's it. So it does this find a good approximation for solving the general Steiner tree. We'll see about that. Okay, in the Euclidean Steiner tree or the metric Steiner tree. So for metric Steiner tree problem, yes, a minimum spanning tree is a good approximation. However, for the general Steiner tree, MST is not a good approximation. We'll see why in the next future slides. Okay. So let's consider this example of Euclidean Steiner tree as I explained. So in this case, yeah, the minimum spanning tree. So on the left picture, you can see we are given an equilateral triangle. As I explained in the earlier example, we use the same image. So the minimum spanning tree includes any of the two edges, right? So the total cost is 2. Hence but the Steiner tree itself, which is the optimal solution, has like a total cost of root 3, as I said earlier in the slide. So thus a minimum spanning tree for at least for the Euclidean Steiner tree at best is like 2 by root 3 uh, approximation. So it is of I mean that's the optimal solution for the Euclidean Steiner tree. In case of metric Steiner tree, obviously minimum spanning tree will cannot be better than 2 by root 3 approximation. However, we can construct a better example like below. Like let's say consider a triangle uh, uh, having each edges of weight 10 and having three vertices, or a square basically having four edges, or a pentagon having five edges. So we can just keep on increasing the number of edges until we form a wheel structure, basically. So we can just keep making this large to n gons, basically. Yeah, a polygon. So so here we have like three cases: a triangle, square, a pentagon. So each n-gon has n required vertices, where each pair of vertices is connected by edges of length 10. Each has a single Steiner vertex in the middle. As you can see, there is an edge from each required vertex to the Steiner vertex in the middle, and each of these edge has a length 5. So from the Steiner vertex to the required vertex, the edge weight is 5, and the edge weight between the required vertices is 10. Okay. So for n-gons, like a polygon, for an n-gon where all distances are 10, a minimum spanning tree has exactly n minus 1 edges, right? And hence the cost would be 10 into n minus 1. On the other hand, the minimum standard tree, which uses the standard vertex here, as you can see in the middle, uh, and it has n edges. Our connecting standard tree has each required vertices, as you can see here. So in this case, it would be 5n, because as you can see, for connecting all of the required number of vertices or edges, we can see the total edges connecting to those vertices is exactly equal to the number of n. So in this case, the optimal solution, the total cost would be 5n, because the weight of the edge for the standard tree, we have assumed it to be 5, at least for this example here. Thus, the minimum spanning tree is no better than 2 n minus 1 slash by n approximation of the optimal spanning tree. So as n gets large, this approaches to a 2 approximation. So it's that is the closest we can get to it suboptimally. So at least for the metric spanning tree, metric Steiner trees, my bad. So finally, it should be clear that minimum spanning tree is like not a good approximation for general Steiner tree problem, but it is a good one for the metric Steiner tree. So let's consider this example, okay? Just to make sure that minimum spanning tree is not a good, heuristic or an approximation for solving the general Steiner tree problem itself. So in this case, just consider the three outer vertices as required, right? The minimum spanning tree has cost as like 3,000, because we'll be connecting all three vertices using any of the two edges. So in this case, the edge weight is 3,000, right? But the optimal solution in this case would be 3, because the edge weight from the Steiner vertex to the required vertex is just going to be 1. So this is like a general case. So we can basically keep the edge weight anything like to our desired range. So that will, at least for the general spanning tree problem. So the minimum spanning tree will always connect the two edges, right? Having more weight. So that is actually not the optimal solution, or not even closer to it, right? Because 6,000 and 3, that's like 2,000 times the optimal solution. That's not what we want. So the minimum spanning tree is not a good heuristic or approximation for solving the general standard tree problem itself. Okay, so let's continue on to the metric standard tree approximation algorithm. So we'll show that basically we'll go through the theorem and the proof itself, and we'll try to show how the minimum spanning tree is the best optimal solution for the metric, best suboptimal solution for the metric standard tree. So for the theorem, we have like set of vertices R and a set of Steiner vertices S. So the required vertices are in blue color, and the Steiner vertices are in red color. And yeah, so throughout the proof, we'll be using this same graph. So this is the graph. As I said, the blue ones are the required vertices, and the two Steiner vertices GH. Those are the Steiner vertices, and all the edges drawn have a weight of 1, and all the edges outside the graph are considered of having a distance 2, basically, outside. So you'll see what I mean in the future slides. So if you want to connect D to B, that's gonna be a weight of 2. That's what is considered, at least for this proof. Okay. So let the tree of vertices V and edges E be the optimal standard tree for some vertices V of, I mean, V being the bigger set, and R and S belong to which is the required vertices, and the Steiner vertices in the subset of V are the subset of V, basically. For example, we have drawn this suboptimal tree, as you can see here from figure A. we have converted this into a optimal standard tree. Okay, so we'll be using the same throughout the proof. So in our example, the cycle. So what the proof says is basically we do DFS because to find the minimum spanning tree, either using Prim's or Kruskal's algorithm. And in our example, the cycle will be as follows: like A to G, G to D, then D to G, then G to F, then back F to G, G to A to H, H to C, C to H, H to B, B to H, H to A again, then A to E, and then E to A. So always we end at the root node, right? So that's how it's shown: A to G, G to D. That's what we see here. Notice that the cycle has like 14 edges, whereas the original tree has 7 edges and 8 vertices. We have already defined the cost T as this, and similarly the cost of the cycle as summation of all the edges basically. So since every edge in the tree appears exactly twice in the cycle, we know that the cost of the cycle is going to be 2 times the cost of the tree itself, right? So in our example, you could see that the cost of the original tree is 8, so the cycle cost is obviously 16, right? Yeah. So the cycle C contains both vertices R and sign vertices S, right? In this case, as you can see here. So we want to basically, if you want to do a minimum spanning tree, this optimal problem, we need to, as we saw here, we need to remove uh, the sign vertices. That's the best solution for minimum. So as you can see here, just ignore all the sign vertices, which is in this case would be G and H, and simply find a minimum spanning tree of required vertices R. So that's what we'll be doing here. So in this case, we'll just try to ignore the vertices G and H because we are solving for the metric standard tree, right? So in this case, it will go like A to D, then D to F, right? Then F to A, then A to C, C to B, B to A to E, and E to A. That's what you can see here. A to D, D to F, F to A. And so in this case, the cost right now will be 15 because which is which was 16 earlier. In this case, it will be 15 because like we have removed a single vertex G. And if we keep on cutting all the vertices, let's say if we cutting G, the cost would be 15. If we cutting H, the cost would be 14. And if we like keep cutting, then eventually the cost will drop. So next step is to like remove the duplicate in the cycle. So in this case, we are going through what we'll do is the first time the vertex is visited, we mark it as new. Mark every other instance of the vertex in the cycle as old. So once we have removed all these standard vertices, and when we are doing the minimum spanning tree problem, we'll need to basically remove all the repeating vertices in the minimum spanning tree. Okay, so as with the standard vertices, now we have like removed all those. We are now basically we just uh, start cutting out basically cutting out the edges. So in this case, the new cycle will be like A to D, then A to D, then A to F, then F to A to C, then C to A, then A to B, B to A, then A to E, and E to A, as you can see here. A to E, then E to A. So in our example, the A is getting repeated a lot, right? So we'll remove the A from consideration. So this leaves us like vertex. So this is how what I was talking about. So we'll just directly keep switching between the edges to find the minimum spanning tree. So the cycle will be if we like remove the old vertices which are like repeating in this case. In this case, it will be the second A and the third A in our cycle here. So if we remove those instances, the cycle would be now A to D, D to F, then F to C, which is an outer edge, that's where the cost is 2. Then C to B, again an outer edge, the cost is 2. B to E, and then E to A itself. So the total cost comes out to be 11, which is again, which is no like, greater than the original cost, which is 16. So the revised cycle here, as you can see, is here. So now we have a cycle where the cost C is less than or equal to 2 times the cost D, right? And every required vertex, which is A, F, C, B, E, we have in the minimum spanning tree, right? So I mean, we have it. So which is basically in our example, it is the minimum spanning tree itself. Has the cost of 9. If we keep adding like 2 plus 1 plus 2 plus 2 plus 2 plus 2, that adds up to be 9. So that's 4 twos and one single one. So the the spanning tree cost is 9, and that is a minimum spanning tree. So that's why we can say for the metric spanning tree, the minimum cost, I mean, the optimal solution will be the minimum spanning tree itself. Okay. Now let's consider how will you solve the general spanning tree problem using the metric spanning tree algorithm, which we just saw with the same proof. So in general minimum spanning tree, as we saw, it's not a good approximation. So what we'll do is basically begin an instance of the general sanity problem via reduction. We'll reduce the, construct a new instance of the metric sanity problem, solve the metric sanity problem using our existing algorithm, which we saw, and then convert the metric sanity instance back to a solution for the general sanity problem. Yeah, so that's how we will solve it. Basically, reducing the general sanity problem to a metric sanity problem and solving using our own algorithm, which we saw, which is in this case will be a minimum spanning tree, right? And then uh, so let's consider, so that was the proof for general standard tree approximation algorithm. Now we'll go through some applications of the standard tree problem itself. Well, it has like vast applications in network design. So AT&T uses a version of standard tree problem called price correcting standard tree problem, which effectively saved them billions of dollars. So it's like it the price correcting standard tree problem has like it has to pay penalties if it wants to include a separate node in the optimal solution. Then so that's how they, so basically let's say in case of AT&T, they if they want to give connection to a user in California, but they don't have towers there, so they'll just ask another vendor to uh, give the service to the customer, and then they'll just pay the uh, Verizon. In this case, they don't have the installation costs itself, so that's how the penalty thing works. So they have to pay a price to the Verizon, but they don't have to install a new node itself. So they just leverage other people's infrastructure. In VLSI design, for reducing the circuit space on board, the route cost of the wires, and reduce the overall time for signals, right? In telecommunication, to reduce the cost of underground wires for the setup itself. Yeah. So these are the sanitary. This was the sanitary problem, and it has like good applications. So thank you. And from here on onwards, my next teammate will continue with the presentation. Thank you.
Hello, my name is Moina, and for this part of the presentation, I'll be explaining load balancing and scheduling with approximation algorithms. Approximation algorithms can be utilized to schedule tasks, allocate resources, and balance loads in data centers, cloud computing, and other fields. With efficient utilization of resources while providing a acceptable quality of service, it is acceptable if it makes some one-sided errors. In particular, with networking, load balancers are used to ensure information systems not lag and, in worst cases, fail from excessive handling of traffic. Besides networking, list scheduling is also used in other fields, like in manufacturing and data centers. It schedules then when jobs will be executed on machines to optimize the production process, while also minimizing the overall load on any of these machines used. And then with vehicle routing, we can optimize the assignment of deliveries and pickups to vehicles, reducing travel time and fuel consumption. So the simplest of all load balancers is the round robin technique. So the load balancer sends the same amount of requests to each server available by cyclically distributing incoming requests to a group of servers. So this load balancer is ideally used when information system servers have the same capacity because there is a higher likelihood of servers overloading or failing, while higher capacity servers remain idle during use. So here on the right-hand side is just a simple visualization of how the round robin works. So first, the end user sends a request or task to the load balancer. Then it sends those requests to the first server, and then the second, and then the third, and then so on until you fill up all the servers, and then it will go back to the first server and repeat the process until all the requests have been distributed throughout all the servers. So although round robin is not an approximation algorithm in itself, it's going to help provide a fundamental foundation to tackling the subproblem of list scheduling. So list scheduling provides a computationally efficient approach for scheduling tasks, but it doesn't guarantee optimal solutions. It aims to find schedules with a performance guarantee based on an approximation ratio. Despite not always yielding optimal schedules, list scheduling's approximation guarantees and efficiency and are valuable in scenarios where finding an optimal solution is impractical due to computational constraints. So before getting into the proofs of list scheduling, here are some common terms that are going to be used throughout the rest of the presentation. C approximation is C times the opt, where C is the cost and opt is the optimum cost. where C less than 1 is the maximization problem, and then when C is greater than 1, that is a minimization problem. An offline algorithm has access to the entire input data from the start of the algorithm and is able to pre-process that data before making decisions, while on the opposite side is online algorithms. So online algorithms make decisions immediately upon receiving each piece of input data, often without incomplete information about the entire problem. And then finally, we have makespan, which is just the maximum load on any machine. So the generalized parameters that a list schedule will take as input is m number of machines, n number of jobs, and then a set of processing times, T1 all the way to Tn, corresponding to the number of jobs. And then Tj is the processing time of job j on any machine. The load of the machine I is makespan I equal to the sum of all processing times assigned to that machine I. So getting to list scheduling now, we can assign jobs to each machine in such a way to minimize the make span. So our first claim is that load balancing is NP hard even with two machines. We will prove this using the greedy algorithm. So we will keep n jobs in a fixed order and then determine the machine with the smallest load before assigning job j to said machine. So here's the pseudocode for implementing list scheduling. So first it takes the parameters m machines and jobs and then the processing times for each job. And then in the first loop, each machine is initialized to not have a load or any jobs yet. And then in the second loop, we check which machine has the smallest load before assigning the current job j to machine I. And then the new load of the machine is computed by taking the previous load and then adding the processing time of job j. So overall, the time complexity of this algorithm will be big O n times log n because of the for loops, and then we're going to be using, you could use a priority queue to find the smallest load of the machines. So I'm going to create a small visualization of how this set of jobs would be scheduled between three machines. So initially, these machines are empty, and then we're going to start with the first job. We can place it into any machine since there are all at a load of 0. So in this case, we're just going to put it in the first machine. And then the second job can be put in either machine 2 or 3 since they have the smallest load now. So we'll just put job 2 into machine 2. And then for the third job, we can only put it into the third machine since it's still at a load of 0, which is the minimum. So now we have machine 1 has load 1, machine 2 has load 2, and then machine 3 has load of 3. When we reach job 4, it will be assigned to machine 1 as it has the smallest load now. And last but not least, we reach job 5, and that will be assigned to machine 2. Now, with all the jobs assigned to a machine now, we can see that the make span is 6 time units because that's the maximum load of machine 1, which is the time 1 from job 1 plus the time from job 4, which is 5 time units, and then that's how we get a make span of 6. And so although each job has now been assigned to a machine, we need to consider now like if it's truly optimal and if there's any worst case scenarios. So with this example in particular, we can see there is a worst case in which we reach the end of the set of jobs, and one of the jobs has a long processing time towards the end of all our assignments to machine. So now this is the same set of jobs, but in this example, we can before we even start the algorithm, the jobs are sorted in decreasing order of their respective times before the algorithm is started. So for this example, the order of jobs is now going to be 4, 3, 5, 2, 1, while the first order was originally 1, 2, 3, 4, 5. Although the make span for this one is only 5 time units, which is not significantly faster than our make span of 6 time units with the original list scheduling, it should be noted that on a bigger scale with more machines, more jobs, and jobs with longer processing times, the order of the jobs based on time will make a much more significant difference. And another thing to note is that the list scheduling and the longest processing times first algorithms are offline algorithms, which will provide faster approximation times and are much closer to the polynomial time because of all the times are available at start time. Moving from offline algorithms, I will now explain this online algorithm, as very often the data for input is not known ahead of time in the real world. So this is the greedy algorithm with a two-cost approximation algorithm. And in order to prove it, we must first compare the solution of the algorithm to the optimal makespan, which we will call L star. And then there are two obvious lower bounds for L star. The first lemma is that the largest job must be assigned to some machine, and that the second lemma is that at least one of the machines has to process the total processing time over M. And continuing this proof, J is going to be the last scheduled job on the machine, I, and then a machine has the maximum load, Li. So the maximum load minus the processing time of the last scheduled job is the load of the machine I before J was assigned. That would be the left side of the line of the machine I in green, and then the last scheduled job is the red bar on the right side of the line. So the load before job J was assigned is less than the load of any other machine K. And then this is true if you recall from the basic list scheduling algorithm that a job is assigned to a machine with the least load. And then next we sum all the loads of the machines over M machines, which can be reduced to the sum of all the processing times over M. And now we can apply lemma 1 and 2 from the previous slide to simplify our inequality. So since Li minus the processing time of job J is less than or equal to at least one of the M machines doing at least a 1 over M fraction of the total work, we can say that is less than or equal to our optimal makespan L star. And since some machine must process the most time-consuming job, that is also less than or equal to our optimal makespan L star. Then if we add those two together, that's how we conclude that this greedy algorithm is a two-cause approximation algorithm. And then due to the restraint on time, I will not be going over detail about these approximations, but would like to mention that Graham was able to optimize list scheduling even further. So I did demonstrate the longest processing time first earlier in the slides, but Graham was able to mathematically prove how the longest processing time is a 1.5 cost algorithm and prove how the same algorithm can be reduced to 4 or 3 cost algorithm when using n machines and 2m plus 1 total n jobs. That's the end of our presentation, and I'd like to say thank you, and please leave any comments or questions on the discussion post on Canvas. Thank you.